There are three main ways that water moves in our ocean basins: waves, tides, and currents. Let's go through those three. The first is waves. All three of them are generated by different processes. We're going to talk about those processes as we go along. Waves are generated by wind. Wind blows from high pressure to low pressure. Those pressure systems are created by differences in heating on the Earth's surface. So high to low pressure, when that happens, the atmosphere is moving. The wind molecules, the gas molecules are moving. They have friction with the surface of the ocean, and they create little capillary waves. As the wind continues to blow, those little waves get bigger and bigger. The biggest waves, like what we call a fully developed sea, that occurs when the wind is blowing at a high speed over a long amount of time. And this last term, fetch, is the open water distance across which the wind blows. And when all those are at their max, then you have what we call fully developed seas, big waves. The waves come in, and the wind is blowing at a perpendicular to them. So here are the wave crest coming into a shoreline and breaking. The wind direction is perpendicular to the wave crest. The waves are moving the water in little orbitals. There is a wave base below which there is no wave motion, and the orbitals are small near wave base and get larger at the Earth's surface, giving us crest and troughs. The difference between a crest and a trough is the wave height, and the water molecules, just like these ducks, are moving in circles. They're not moving from one side of the image to the other. They're just kind of moving in this circle, kind of up and down motion. You can click this link here and I'll show you ducks that are moving in up and down instead of side to side. Okay, so here's that wave base again, and wavelength is from a crest to a crest. Wavelength is from crest to crest. Wave base is 1/2 of that wavelength. So there are waves out here at sea that their size is dictated by that wave duration, wave speed, and the fetch, and those are open water waves. When the waves get closer to the shoreline, they're going to start to feel the bottom because wave base intersects with the shoreline. When that happens, there's drag. So the bottom of the wave is going to experience drag. The wave, instead of being this broad wave coming in the shoreline, it's going to start to compress as it experiences that drag. And so the volume of water is going to go into the height of the wave. So the height of the wave increases as the wavelength decreases. And then when it gets into the shoreline, the top can overtop the base, and that would be breaking wave. Okay, so here is that image again. The waves out at sea have these nice orbitals. As they are coming into shoreline, the orbitals get a little bit more side to side motion to them. A swell is these storm waves coming into a shoreline. We have where they start to get steep, the surf zone, and they're going to break, and then after they've broken and they just roll up the shoreline, that's the surf zone. I mean the zone that is getting to the swash zone, where the waves are coming up the beach but swashing back down into the ocean. Okay. Here we go. So the breakers are out here. The surf zone is here, and the swash is these little ripply waves that come into the shoreline. All right. The wind doesn't always blow straight into the shoreline. It blows at an angle to the shoreline. So these black arrows are called orthogonals. They are drawn perpendicular to the wave crest. So these light color lines are the waves coming into the shoreline, perpendicular to that wind direction. So the black lines are wind direction and perpendicular to the wave crest. Because that leading edge of the wave is hitting shallow water before the trailing edge that's still further out to sea, those waves are going to refract or bend as they come into the shoreline. That's wave refraction. So wave refraction can have a couple consequences. One is it can act to concentrate wave energy on a headland. So as these orthogonals, those perpendicular black lines, come into the shoreline, they're coming together on that point, and that is focusing in that energy, so there will be erosion there. Those orthogonals here at number 9, the waves are coming in and spreading a little bit, so the wave energy is a little bit more dissipated there, so that creates a sandy beach. So this is what that looks like on the beach in Oregon, this continental margin, active continental margin we saw before. Sandy beach, and then these arrows here that are coming in and focusing that energy on the headlands. There's headland erosion and deposition here on the sandy beach. Tides. These are the result of the gravitational pull between the moon and the sun. Because the moon is closer to the earth, there's more influence from the moon than there is from the sun. But sometimes the moon and the sun, they team up and they give us high tides and low tides. So this is high tide, is the high tide line. Mean sea level is between high and low tide, and then low tide is the low tide. All right, what are tides? You kind of think of them as this rise and fall of the ocean. But what you could think of it, you stand back a little bit from the earth, way back, and it's actually this wave that goes around the earth that is pointing towards the moon. So imagine a giant wave pointing towards the moon because it's being pulled by the moon. And there's another force over here because the earth is spinning. There's two bulges, one on either side of the earth. And as the earth rotates and as the moon orbits around the earth, that bulge of water, that envelope of water, is pointing towards the moon. And sometimes the sun lines up with the moon and we get what we call spring tides. So here at the bottom are the spring tides, where the sun, the moon, and the earth are all three in alignment. There's two different times there that happens. Sometimes the moon can be on the other side of the earth from the sun. And at the top is the neap tide, where the moon is at a right angle to the sun, and so the sun has its pull of gravity on the ocean basins, and so the high tides and the low tides, there's not as big a difference between high and low tide during that time. Okay, what do all these words say? All the things I just said. Sometimes, so the alignment of the sun and the moon have an effect, but also the topography can have effect on the magnitude of the tides. The earth is rotating within that bulge of water. Spring tides, solar and lunar tides are in phase, so that they're in alignment. And the neap tides, they're at right angles to each other. Tide charts look like this. This is a Hurricane Ida in 2009. Normal high and low tides, but are in blue. And then when the hurricane came through with the storm surge, now we had much higher high tides and higher low tides. Both of them were just high. Here it is also that same hurricane in the Atlantic, over on the Atlantic side, not the Sound side, and the effect of the hurricane coming through and changing the tides. But the blue is the normal tidal tides.